Hello and welcome to our coverage of Alberta's Algebra number 4 outcome for Math 10C, specifically dealing with the distributive property. We'll go through our curricular outcomes, review the 13 rules of algebra, and then deal with the distributive property in detail before doing examples and exercises. So our particular curricular outcome is to demonstrate an understanding of the multiplication of polynomial expressions, limited to binomials, monomials, and trinomials, concretely, pictorially, and symbolically. If this is your first time through Math 10 and this content, you are not expected to know what the terms monomials, binomials, and trinomials mean yet. We will define them, though not in this video. Now, let's review the 13 rules of algebra dealing with real numbers. When you're dealing with real numbers, there are only 13 rules. Now, 12 of these have been introduced before. The distributive property we're dealing with today, also part of the review, is usually the last one introduced, even though it's not the last one in the order I have written. You've probably seen all 13, although most grade 10 students have never had someone sit down and say, these 13 cover it all. That part may be new. When you get to more advanced algebras in the future, they'll become more challenging not by adding rules, but by taking these rules away. It's actually almost impossible to add rules without breaking everything. Right, so rules you are used to that you won't see here, such as 0 times x equals 0 for any x, are actually consequences of these rules and not separate rules in themselves. There are also some definitions. You won't see exponents defined here, but if you write x cubed as x times x times x, it'll follow all of these rules. So the rules themselves. Rule number 1, the sum of two numbers is a number. The most surprising thing about this rule is that we actually bothered to write it down. And we write it down because without it, we just couldn't function. If 2 plus 2 equals elephant, just give up. Our second rule, the product of two numbers is a number. We'll actually see a pattern like this for the first 10 rules, where there's an addition rule for an odd number, and then the corresponding multiplication rule in the next even number. For example, addition commutes. The order does not matter. A plus B is the same as B plus A. 1 plus 2 is 3, as is 2 plus 1. The matching multiplication rule says that you can multiply in any order. 2 times 3 is the same as 3 times 2. Both are 6. Next, we have what we call the associative property. If you're adding three numbers, you can pick which two you associate with each other to add first. So 1 plus 2 plus 3. If you do the 2 plus 3 first, you get 1 plus 5, which is 6. If you do the 1 plus 2 first, you get 3 plus 3, still 6. Corresponding multiplication rule. Yep, you guessed it. You multiply three numbers, you could start with any pair first. So if you say take 2 times 3 times 5, you can go 2 times 15 to get 30, or 6 times 5, still 30. All right, rule number 7. It's what we call the additive identity. When you add 0 to something, you do not change the identity of that something. Anything plus 0 is the first anything. For multiplication, we can't use 0 for this. We use 1. Anything times 1 is itself. It's about maintaining the identity. Up to this point, if you did not already know the symbols plus, times, 0, and 1, if I scrap them and replace them with marshmallows from Lucky Charms, you've got hearts, moons, clovers, diamonds, you would not be able to tell what was addition and what was multiplication. It's rules 9 and 10 that make it clear which is which. Every number has a negative, so that a number plus its negative or its additive inverse is 0. So a plus negative a is 0. Subtraction is just a shorthand of this. So when we have a plus negative b, we write that as a minus b in a shorthand. Now, how can we tell these apart? It's because the multiplication version has an exception. Every number other than 0 has a reciprocal, so that a times its reciprocal, its multiplicative inverse, is 1. Notice 0 was the additive identity, 1 is the multiplicative identity. So division is a shorthand. A times the inverse of b gives a divided by b. So here is where we can tell them apart. 0 has no multiplicative inverse. So if you have a complicated system where your mathematical objects are not just on a number line, this is how you can tell which of your operations is addition and which is multiplication. The 11th rule. This is the distributive property. It's the big one for today. This is how multiplication and addition combine, because up to this point, we've only seen one or the other. If you have something outside the brackets multiplied by two things in the brackets, you multiply what's outside by each of the things inside. You have to make sure you get them all. You can have 15 things in the brackets. It has to multiply by all 15. It distributes through those brackets. Now, these 11 rules actually define what we call an algebraic field. Rules 12 and 13 will narrow things down specifically so that we are dealing with the set of real numbers that was defined in an earlier lesson. So one is officially known as the well-ordered principle. All numbers fit on a number line. So if a is less than b and b is less than c, a is also less than c. You can't have rock, paper, scissors structures. Those are forbidden. The last rule is that the number line has no gaps. Rule number 13 is the one that tells the difference between the rational numbers and the reals. The rational numbers have gaps on the number line. Pi is irrational. The square root of 2 is irrational. So that the rational numbers leave gaps. The real numbers are when you close those gaps. All right, so how does this work in detail? Well, if we look at the list of rules, this is the one that deals with addition and multiplication together. So one of the first actual applications we had of multiplication was the area of a rectangle. So let's picture a plus b times c plus d as the area of a rectangle with a length a plus b and a width of c plus d. If we draw that rectangle, we can break it into 4 sections. One will have area AC, another AD, BC, and BD. Those come from doing our distributive property. So multiply a plus b across the brackets, we get a plus b times c and a plus b times d. Now we keep going, multiply the c through that brackets, we get ac plus bc, and our second set of brackets gives us ad plus bd. Same 4 terms, different order than what I listed in bullet point 3, but the same 4 terms. If you are multiplying a polynomial with n terms by a polynomial with m terms, you should have n times n terms in the result before you start collecting like terms. So if you have 3 terms in one polynomial and 5 in the other, when you multiply them, you'll have 15 terms. Now, they may simplify to a lot less than that. When you collect like terms, some might add up to 0, some just have the same exponents. So your last step is probably going to have less than 15. At least it does in most cases. But you should start with 15 before those like terms are collected. Right, so here is what that rectangle would look like. So the top, that bar across the top, a plus b. The side, that's length c plus d. Our top left rectangle, when we chop it up, has area AC, bottom left area AD, top right area BC, bottom right area BD. So let's look at examples. Let's multiply here and collect like terms. We want to take each term in the left bracket and multiply it by each term in the right. When you have 2 terms times 2 terms, that's 4 terms, there is a FOIL acronym for first, outside, inside, last that is useful. That is only useful for 2 terms times 2 terms, so I don't use it much. All right, let's multiply these out. So, if we start with the first terms, 3x times 2x, 3 times 2 is 6, x times x is x squared, we get a 6x squared. Our second term, we take the terms on the outside, 3x times negative 7. We keep that negative sign, 3 times 7 is 21, and we have an x. So these become negative 21x. Now, our inside terms, positive 5 times 2x, 5 times 2 is 10. This gives us 10x. Our last terms in each bracket, plus 5 times negative 7, positive 5 times negative 7 is a negative 35. 2 terms times 2 terms gives us 4 terms. Now we collect our like terms. All right, to collect them, we look at the exponents. 6x squared is the only term where the exponent of x is 2. So that just gets copied right over. Next, we check the exponents where x is 1. We have 2 terms that are x to the 1. So we have negative 21x's and a positive 10x's. Negative 21 plus 10 is negative 11. And that's how many x's we have. So these collect to be negative 11x. We cannot collect them with the x squared term. We have to have identical variables with identical exponents to collect our like terms. Finally, our constant term, the only term without exponents, is a negative 35. So 3x plus 5 times 2x minus 7 is 6x squared minus 11x minus 35. Example 2, let's compare 3x plus 1 to 2x plus, or times 2x plus 7 to the product of 31 times 27. Well, when x is 10, they're identical. So it's the same structure. If you were to multiply 31 by 27 by hand, you'd go 7 times 1. That's our last terms. Then you go 7 times the 3, but leave it a space over for the place value. That's 7 times 3x. So now we have our last, we have our outside. We'd put in the placeholder and then go 2 times 1. That's our inside. And finally, 20 times 30, that's our first. So in the special case where x is 10, the 2 calculations are completely identical. You can check that. If you have a number, you're multiplying these out, pick a specific value of x, multiply it with the brackets, and substitute it into your answer. Make sure you get the same value, preferably with more than one number. Try to pick at least a prime number that doesn't otherwise appear in the problem. All right. Example 3, multiply and collect like terms. We have 2x minus 1, and then it's cubed outside the bracket. Well, that means we're going to take 2x minus 1 3 times and multiply them all together. So 2x minus 1 cubed is 2x minus 1 times 2x minus 1 times 2x minus 1. We're going to start by multiplying the first 2. So we're leaving our third there, and we're leaving the space. First terms, 2x times 2x. That's 4x squared. Now we're going to take our 2x and multiply it by the negative 1. So now our first 2x has been multiplied by everything out here. 2x times negative 1 is a negative 2x. The 2x terms are accounted for, and now we need to deal with negative 1. Negative 1 times 2x is another negative 2x. And negative 1 times negative 1 is a positive 1. Before we multiply, let's collect like terms. If we multiply them now, 4 by 2 is 8. We'd have 8 terms floating around. If we can collect them first, then we might be able to reduce that number. 4x squared gets copied over. Our negative 2x and negative 2x become negative 4x. And our negative 1 is the only constant, so that just gets copied over. So there, we have just reduced ourselves from 8 terms to 6. Again, first terms, 4x squared times 2x. 4 times 2 is 8. By our exponent rules, x squared times x to the 1 is x to the 2 plus 1, which is x cubed. Now, 4x squared times negative 1 gives us a negative 4x squared. That's our 4x squared multiplications. A negative 4x times a negative 2 is a negative 8x squared. We have 2 x's now. Negative 4 times negative 1 is a positive 4x. 1 times negative 1, 1 times 2x. We have to do all the terms. I almost missed the first one. That's a plus 2x, and plus 1 times negative 1 is a negative 1. All right, now we need to collect all of our like terms. Going exponent by exponent, because we can only collect when you have matching exponents with matching variables. We only have one x cubed term. That just gets copied over. We have 2 terms with x squared, the negative 4x squared and the negative 8x squared. Negative 4 and negative 8 make negative 12. 2 terms that are linear in x, 4x and 2x, combine to make 6x. And finally, negative 1. All right, exercises. Your chance to give this a shot. Multiply and collect like terms. Pause now so you could take whatever time you need. Think about how many terms you should have before you simplify. So you should have them multiplied. If by now, actually, you should have paused and had the problem finished, but make sure you multiply and collect like terms. When you've multiplied and collected like terms, you should get 20x squared. That's the 4x times 5x. A 13x from negative 15x on the inside, and a positive 28x on the outside. And negative 3 times 7 is a negative 21. Exercise 2. Multiply and collect like terms. We did an example very much like this you might want to go back and use as a model. Now pause and take whatever time you need. All right. In the end, x minus 5 cubed becomes x cubed minus 15x squared plus 75x minus 125. When we finally learn about the binomial theorem and the binomial terms, we will actually be able to take x minus 5 to any exponent and just go straight to writing down the final answer. All right. Last exercise, multiply and collect like terms. Notice that both of these binomials are squared. We're going to have 4 of them multiplying here. So 2 times 2 times 2 times 2. If you save all your simplifications to the end, which I don't recommend, you will have 16 terms to collect with only 5 different exponents. I do recommend collecting like terms as you go to reduce the total number of terms you're dealing with. Pause now to take whatever time you need. All right, and this is a 4x to the 4th plus 20x cubed plus 13x squared minus 30x plus 9. In summary, the general form of the distributive property is A times the sum of B and C makes A times B plus A times C. The distributive property is true even if A, B, and C are polynomials rather than simple numbers, but you may need to apply it more than once. The product of a polynomial with m terms and a polynomial with n terms will have m times n terms before the like terms are collected. If you have any questions, any feedback, leave them in the comments, and I will do my best to get back to you in a timely fashion.